More of section 5.4. Today we're going to look at the average value of a function. In the past we used many rectangles to estimate the area under a curve. Today we're going to explore a slightly different question. Is it possible to find one rectangle that has the same area as the area underneath the curve? And if so, how do we find this perfect rectangle? So let's think about, can we find one rectangle that has the same area as the area under the curve? Well, sure. In the same way that you could have a square and a circle that have the same area, right? We can have an area of a curve and an area of a rectangle that has the exact same curve. Looking at number 1, the graph of f of x is shown on the interval from 0 to 4. Explain why the area underneath the curve is more than 4, but less than 20. Let's look at this in terms of rectangles. If we were to have an area of 4, well, if it has a length of 4, then it would need to have a height of 1. So we would be looking at basically this rectangle. And this rectangle is obviously too small of an approximation of the area under the curve. An area of 20, well, again, my base is 4, so it would have to have a height of 5. That would be this whole rectangle here. And obviously that covers area that's outside of my rectangle. So obviously 20 would be too high of an estimate. Number 2, do you think the area underneath the curve is more than 8? Less than 16? How can we figure this out? Well, again, if we look at an area of 8, we would go up to this height of 2. Well, this will only have a little bit of area outside of that, so that's obviously going to be not big enough of an area. And if we come all the way up to here to 4, so we have a square 4 by 4, this area that's outside here is probably more than what we have left for in there. So 8 is going to be too small, and 16 is going to be too big. So at what height do you think we should draw the rectangle so its area is exactly the same as the area under the curve? I'd like you to make your own guesstimate up on that graph and label that height C. And now we have two different methods for getting the area under the curve. I'm not going to label where I think the C would be. We're just going to find where that C would be. So write an expression that would give the area under the curve in terms of the perfect height. Well, wherever you put your height, the width is still 4, so the area of the rectangle would be base times the height of C. In part B, write the integral expression that gives the area under the curve. And what can you say about the expression and the expression in question 4a. So the area under the curve, well, my curve, the area is the integral, and I'm going from 0 to 4, and this curve has been named f of x. So this curve is the integral from 0 to 4 of f of x dx. And what can I say about this expression is that it's going to be equal to 4c. And why is it going to be equal to 4c? Because we chose 4c to have the exact same area as the area under the curve. So based on how we chose our c, we know that they have to be equal. If we are given that the function is negative x squared plus 4x plus 1, find the value of the perfect height of c. So we want to find from 0 to 4 f of x dx. So we're going to integrate this equation. So negative 1/3 x cubed plus 2x squared plus x, and we're going to evaluate that from 0 to 4. So now I'd like you to pause the video and evaluate that function from 0 to 4. Remember, to evaluate this, I'm going to plug in the 4 and evaluate it at the upper level of integration. Minus, and I'm going to plug in the 0. And since each of these terms have 0, then obviously I'm going to be subtracting 0. And if I do all that handy-dandy math, I get that the area is 14 2/3. Now remember, we let that integral equal 4c. So 4c equals 14 2/3. And if we divide by 4, we find that c equals 3 2/3. So I can come back up here, and roughly at 3 2/3, this would be my rectangle. That would have the exact same area as the area under the curve. I could say that c equals 1/4, because I divided the area by 4, of the integral 0 to 4 of f of x dx. How does the value of c that we just found compare to all the values of the function f of x over the interval from 0 to 4? Well, it's in the middle, isn't it? It's slightly closer to the max value of 5. It's closer to that max value of 5 than it is to the minimum value of 3. In fact, c is the average value. The average value of a continuous function f of x on the interval from a to b is the height of the rectangle that encompasses the same area as the area under the curve. So in other words, if I were to find the area of that rectangle, the height is c times the length of my rectangle is the distance between b minus a, and that's going to equal the area under the curve, so the integral from a to b of f of x dx. In order to find my average value, find that c, if I multiply by the reciprocal, I find that my c is 1 over the length of my interval times the integral of f of x dx. And I tried to draw a picture where you could see how this would kind of work. So if you notice, this area that's not included in my rectangle is compensated for this area that's included in my rectangle. Normally when I find the area under the curve, I would need that area and not that area. So hopefully you can see how those two areas kind of compensate for each other, and so we have that average value. Problem number 1. Chipotle gives a BOGO burritos on Teacher Appreciation Day if you're willing to stand in line. On this particular day, the number of people waiting in line in order to order is modeled by W of t, where t is measured in hours since Chipotle opened at 11 a.m. Write an integral expression that would give the average number of people waiting in line at Chipotle from noon to 6. So the average value, so I'm looking from noon to 6, that encompasses 6 hours, so 1/6 of the integral. If we're counting from noon, Chipotle's already been open for 1 hour, and to 6 p.m. would be a 7-hour total window that they would be open. WT dt. Number 2, find the average value of the function g of x equals 3x squared minus 4x on the interval from 1 to 4. So again, my interval is 4 minus 1, and I'm looking at the integral of 1 to 4 of 3x squared minus 4x dx. This is 1/3, and then if I take the integral, 3x squared is going to be x cubed minus the integral of 4x is going to be minus 2x squared. And I'm going to look at this from 1 to 4. I'd like you to pause the video and see if you can find that average value. So 1/3, plugging in the 4, I'm going to have 64 minus 32 minus, plugging in the 1, and I'm going to have 1 minus 2. Doing the math, I get 1/3 times 33. So my average value is 11. And example number 3. The temperature of the water in a bathtub is given by W of t, a strictly increasing differentiable function. Use a trapezoidal sum to approximate that average value. So 1 to 20. And I would like you to pause the video to see if you can write out that trapezoidal rule. So remember, base 1 plus base 2, 55 plus 57.1. So base 1 plus base 2 divided by 2. And then the height of that rectangle would be the interval from 0 to 4, so 4 units. This is what you should get when you write them all out. Then doing our math behind them, the arithmetic, calculating each of them individually. So then I have 1/20 times 1,257.8, When I multiply those, I get 62.89. Using proper units, interpret the answer in your Part A in context. What does this mean? Well, this means that the average temperature of the water in the tub between t equals 2 and t equals 20 minutes is approximately 62.89 degrees. And that takes care of an average value of a function. If you have any questions, as usual, I look forward to seeing you in class. Even if you don't have any questions, I look forward to seeing you in class.